Welcome. This is Dr. Morton, and this is the introduction or the overview for Logic Design Chapter 18. In this, we're going to hopefully try and put it all together. And many of you may be doing logic design, but in very different ways. Some may be working with hardware description language and designing programming FPGAs, or you may be making integrated circuits, or you may be using microprocessors and doing embedded controllers, or you may be using a mixture of hardware description language and computer languages working with an FPGA in connection with a microprocessor, maybe a embedded core, or maybe a standalone processor along with an FPGA. Or you may be doing some sort of other more complicated arrangement. But in any event, you will no doubt be working on a whole different range of things. All right, so this is chapter 18, and you can see this is the icon for it. And I think this is kind of cute because we have in the center here a little picture of a little girl who's, you can see she's holding, I guess you can see it. Maybe I'll blow it up here. You can see she's working with a little tablet, and she's holding it with her toes by its handle, and then working on the touch screen side of it there. And if you look at this, you realize this little girl is entirely comfortable with this technology. And that's what we want for you all. We want you to be entirely comfortable with this technology. Okay. So, so the learning objectives. One, we want you to have the ability to design a 4-bit counter that counts a non-sequential sequence of 4-bit numbers that includes at least one repeated 4-bit number in the sequence. So we'll talk about that. We did this in earlier chapters where we created these non-sequential counts, but we weren't allowed to have two of our counts be the same. And the reason for that is we would have to have used a different design technique, and we'll get to that in this chapter. I want you to be able to design a state machine for a little bit more complicated sequence detector. I want you to be able to explain why advanced adders instead of ripple carry adders are essential for modern computing, and I want you to be able to explain why it may not be important to simplify our logic expressions if we're designing, say, for an FPGA as our hardware target, but if we're designing for an integrated circuit or maybe other targets, other FPGAs using different topology, then you might need to be, it may be very important to simplify your logic expressions. And finally, to be able to explain why it's important, so when it's important to simplify our logic expressions and when it isn't, basically, or at least some sense of that. All right, we have some terms here. Timing closure is one that I wanted to talk about briefly. I'm not going to cover it actually in the text, but this whole issue of timing closure is really important when you're designing an integrated circuit, or when you're implementing a project with a FPGA, or when you're designing an embedded design. And what you find out is that if your product isn't as fast as it needs to be competitive in the marketplace, you're really going to have a tough time selling it. All right, so timing closure is defined as when designing an IC, part of the design criteria includes targets for how quickly the system must produce results from new inputs. In today's market, an IC that's faster than its competition will typically command a larger market share, whereas a slower chip will become a legacy IC over time. For this reason, new designs have speed performance goals that must be met to have a viable product. And when these goals are met during the design process, we call it timing closure. And this is worked out and tested using the simulation features of our design tools. All right. Circuit area just has to do with the real estate required for your design. And then one of the advanced adders, we'll talk about it briefly, is the carry look-ahead adder. And we won't go into great detail to understand exactly how it works, but we want to just kind of look at it so you're familiar with the term, and then later on in say, digital systems design course, you may encounter a device like this and have to understand it in much more detail. Okay, so let's first look at this non-sequential counter. Now for this, I think I'm gonna switch to let's see. I'm gonna didn't do that. That's what I wanted to do. Okay, so we'll do this. So I'm going to do the slides, and then we'll come back to the book maybe in a bit. All right. So I've already been over these learning objectives. So and remember that we talked in the last chapter about designing algorithms, and for many of these learning objectives, figuring out algorithms is an important part. Okay, so a non-sequential counter with a repeated sequence. So what I mean by that is, here's our count sequence. And I talked about doing it in 4 bits, but actually this is a 3-bit count sequence here. So 0, 1, 0, or 2, then 7, 6, 5, 3, and then 6 again, and then back to 2. So 2, 7, 6, 5, 3, 6, and then back to 2. All right, so the problem here is that when the flip-flops are at the count 1, 1, 0, which occurs in so this would be S1, S2, S3, or S0, S1, S2. So this would be an S2, or the third sequence, or S3, 4, 5, or S5. So how do you know whether you're in S2 or S5 when your flip-flops are 1, 1, 0? Well, the answer is it's the same. It's the same designation, so there's no way to tell whether you're in that third sequence or the sixth sequence, S2 or S5. So how could the circuit know what the next state to go to would be when you're at 1, 1, 0 if you don't know whether you're in the third or the sixth sequence? Well, we have to have a more complicated design. What we really need to do to make this work is to add an output matrix to hold our desired count sequence values, and then just number our states S0, S1, S2, S3, S4, S5 in straight binary order. So our first state, our present state would be 0, 0, 0, and our desired next state would be 0, 0, 1. But our output matrix, when we're in state S0, would display 0, 1, 0. Okay, so here's what this is going to look like. Our present state, 0, 1, 2, 3, 4, 5, and then 2 don't care states, 6 and 7. And our desired next state, from 0 it's 1, from 1 it's 2, from 2 it's 3, from 3 it's 4, from 4 it's 5, and from 5 it's back to 0. But our desired outputs, and we have 3 of them, F1, F2, F3, this is our desired output sequence, or our desired count state. And we could connect these outputs to, say, LEDs, or we could latch them into flip-flops, although there's a little caution, and we'll cover that in a bit. But if we used LEDs, no problem. We just hook up LEDs to these outputs. And so F1 would drive this LED, and F2 would drive the next LED, and F3 would drive the next. And you could look at the LEDs, and it'd be off, on, off, and here it'd be on, and on, off, and so forth. And then we'd have some don't cares down here to simplify our K-maps. All right, so this is what our state table would be. So now our non-sequential counter has an output matrix, which we didn't have before. We just let our flip-flop states be our de facto outputs without any real outputs. But in this case, we have no input. We have a clock, but we have real outputs now. We have an output matrix. So we have to design the D inputs for our 3 flip-flops, and then we have to have a network for each of our outputs, F1, F2, and F3, which could actually be used to latch in 3 additional flip-flops, which would be our output flip-flops, if we wanted to actually have the value held in flip-flops for some reason. Or we could just drive LEDs or some sort of sensor, some sort of display. Okay. So if we do an SM chart for this problem, we're just going to go S0, S1, S2, S3, S4, S5, and back to S0. Remember, this does not have an input. So since it does not have an input, then we only have one path. We only have to account for one path out of every one of our states. And we only have state boxes because we have no input, so there's no conditional, there's no decision boxes. And since our outputs are associated with our states, so the output in S0 would be 0, 1, 0. The output in S1 would be 1, 1, 1, and so forth. And notice we do have 1, 1, 0 in S2, and we have 1, 1, 0 in S5. But their encoding for the states is just going to be 0, 1, 2, 3, 4, 5. So these have a different encoding. So we know here we're in S1 because our flip-flops are 0, 0, 1. And here we know we're in S5 because our flip-flops are 1, 1, 0, 1, 0, 1. So we do know what next state to go to because here we know we're in S5 going to S0. Here we know we're in S2 going to S3, even though our outputs are identical. Where is it? Our outputs are identical here. 1, 1, 0 and 1, 1, 0. Different in the other states, but identical in these two states, and that's totally fine. Okay. So it's a more because there's no conditional output boxes, and there's no inputs, so there's no decision boxes. The numbers in the boxes are the outputs. The numbers on top of the boxes are the flip-flop encoding of our state, and the states are in straight binary order. Okay, so we can solve this directly from our SM chart. So you know that our flip-flop input equations, our DA is just all the paths into states where the flip-flop is a 1. So if we go back here, what states is the A flip-flop a 1? It's a 1 in S4 and S5 only. So we just need to account for the paths into S4, there's only 1. And the path into S5, there's only 1. And there's no inputs, so there'll be no X's involved. So the path in here is just 0, 1, 1. And the path into S5 is just 1, 0, 0. So we just OR together A prime BC plus A B prime C prime. So A prime BC plus A B prime C prime. And we do the same for DB. In DB we have, it's a 0 here, a 0 here, but it's a 1 there. And it's a 1 here. And then it's a 0, 0. So we have to do these two. So this one comes from here. A prime B prime C plus this one comes from here. So it's A prime B C prime. And you can see that here. A prime B prime C and A prime B C prime. And the DC is the same. It turns out for the C that there are 3 nodes where C is a 1. Here, here, and here. And so we have to account for, we have to OR 3 terms together. And so this one comes from A prime B prime C prime. This one comes from A prime B C prime. And this one comes from A B prime C prime. So that's it. That takes care of our DA, DB, and DC inputs for the 3 flip-flops that are going to hold our next state, or are going to hold our present state. And then our output equations, which are going to display our desired count sequence, F1, F2, and F3, we just OR all the nodes where the output for F1 or F2 or F3 is a 1. So for instance, start with F1. So F1 is 0 here, but it's 1 there, it's 1 here, it's 1 here, it's 0 here, it's 1 here. So we need all the states except for S4 and S0. So we have to have A prime B prime C plus A prime B C prime plus A prime B C plus A B prime C. And that should be here. So we have all these, we have these 4 ORed together. And we probably can simplify this. Haven't really looked at that. And for F2, we need states 0, 1, 2, and 4, and 5. Because F2 is 1 in all those states. 1 here, 1 here, 1 here, 0 there, 1 here, and 1 here. So, so we just need all of these states. And then for C, it's 0, 1, 0, 1, 1, 0. So we need S1, we need S1, S3, S4. So we need 3 terms. And that would be A prime B prime C plus A prime BC plus A B B prime C prime. Which would be here. So A prime B prime C plus A prime B C plus A B prime C prime. All right, and then we can simplify these algebraically. Or we can plot those terms in K-maps and see if we can simplify them, because we do have a couple of don't cares. And here I did the next state, or I did the D inputs for DA, DB, DC. We did include the don't cares here, and we just plotted those terms, and boom, we get these simplifications. And the same thing here. So it's probably good to take advantage of our don't cares. And then we build a circuit. So here's our A flip-flop, our B flip-flop, and our C flip-flop, and these are the inputs. This one was just C prime. This one was more complicated, and this one was moderately complicated as well. And then here's our clock line going into these three. And then here are the output matrix. So for F1, we just needed B plus C ORed together here with this OR gate, B prime ORed with C prime here, and then we needed two AND gates, A prime C ORed with A C prime. And we use these to drive these three inputs. This assumes here that we're going to have three additional flip-flops, so a total of 6, 3 to hold the present state, and 3 to hold the desired output count sequence. But notice here's the tricky problem, and I just want to mention this. So if you look over here, if you think about this, I think I wrote this out on the slide. Yeah. So no, I didn't. I did that more in the text. So let's see. Let me go back to the book. Oh, that timed out. Okay, let's. Sorry. And hopefully it'll come. Yeah, good. Okay. So if we go down here, yeah, you can see there's our present state, desired next state, and our outputs, and then but there is one little problem, and I think I covered it here, but maybe I didn't. Yeah, I think I talked about it up here. I may just let you all read this, and I'm going to try and explain it briefly. All right, so yeah, okay, I'll go back to the. I'll just go back to this then. Okay. Yeah. So if we look back at our slides, so when we want, so this output matrix to drive the correct count relies on the outputs from these flip-flops. So when I put B and C, I'm talking about this flip-flop's output, which is Q here, Q sub B if you want, and this output Q sub C. Well, here's the problem. If we you notice I have some gates here, and I don't know how many gates it really needs to be. But when the clock changes, there's a small time that has to expire called the propagation delay before the new present state is displayed in the flip-flop outputs. So we have the correct inputs here to get to the correct next present state. So if we're in S0, where they're all 0, the next desired state would be 0, 0, 1, for instance. And then if we're in 1, the next would be 0, 1, 0, or 2, and so forth. And when we're at 1, 0, 1, or S5, the next desired state would be 0, 0, 0, or S0. These flip-flop, these output equations here, this output network, relies on these flip-flops being in the correct present state. So if we didn't put a delay in the clock line here, which I know I told you to never do that, but in this case it's required, because if there's no delay, then our desired outputs are always going to be 1 clock cycle delayed, because when the clock hits here, the current inputs for here are going to be our old state, not the new state that we're going to. That won't happen until the propagation delay expires. So if we want these flip-flops to be showing the right outputs for the current state displayed in these flip-flops, we have to delay this clock line and let these flip-flops all change and send out the correct state so that these inputs are appropriate for this state. Otherwise, they're going to still be at the same values before the clock hit, and we're going to latch those in. Or possibly they'll be changing so fast that we'll have a problem. So generally speaking, if we drove LEDs with these, then it would be fine, because in a short amount of time, these outputs would be correct and the LED would be right. But if you're driving a D input to a flip-flop and you're using a clock to latch that in, it's going to latch it at the same time as these change if you don't put a delay in it. So I hope that makes sense. We usually cover that in class some and let students ask questions, and usually takes a question or two to make that make sense. But hopefully you got that. All right. So we only have a clock input and the three non-sequential outputs: clock, F1, F2, and F3. Of course, we also have the outputs for the next state flip-flops, the D sub A, D sub B, and D sub C that we have to generate too. But if we do this in C, we don't have to do that. We just have to generate these clocks. So how would you implement this if you were going to write computer code? Well, so what you do is you have a clock and you have the three outputs. So we have to wait to change the outputs on the falling edge, say, of the clock, or maybe the rising edge, whatever you're going to do. So we wrap the code in an infinite while loop to execute it over and over, and we get the clock from an input GPIO pin, say RC0. We input that, and then we have three GPIO pins that are set for the output: F1, say, through F2, F3. So we let F1, say, be RC1, F2 be RC0, and F3 be RC3. These would represent ports in the C port of the microprocessor. And these would be pins that would actually come out of the microprocessor that we could connect to LEDs, or we could connect those to flip-flops, I guess, if we wanted. The GPIO pins can be set as inputs or outputs, but they can only, if they're inputs, that you can only read a 0 or 1 as an input, and if they're set as outputs, you can only output a 0 or 1. So these pins either input ground, or so let's say we're running the microprocessor at 5 volts. So they represent ground or 5 volts as an input, and you read it as 0 or 1. 0 if it's ground, 1 if it's VDD, 5 volts. As an output, it's either going to output 0 volts or 5 volts. And generally, it doesn't output anything in between except when it transitions very rapidly. And so once it's stable, it's only going to be 0 or 5 volts, say, if that's what the chip's running at. Okay, so here's what the code can look like. If we just did straight line code, we wait here while RC0 is high. Wait here while the clock is high, and we output our first count sequence 0, 1, 0 through our three outputs RC1, RC2, and RC3, or 2. Then when RC0 goes low, we wait here till it goes back high. When it goes back high again, we wait here and we output the new count, which in this case was 111, I think, 7. And then we wait till it goes low, and when it goes back high, then we output the next count, which is 6. And we do the same thing: 5, 3, and then back to 6, and then after that, back to 2. Well, it's an infinite while loop, so it automatically starts back over up here after this one. All right, here we use a little for loop, and we just store our desired output values in a little matrix. Right up here, we call it out, and it has 6 values: 2, 7, 6, 5, 3, and 6. And those are our values. And then we have a counter J. We start J at 0, and we count 0, 1, 2, 3, 4, 5. And when it gets to 5, we do it again. And then here are our outputs. Our outputs are J would be we take the output number here. In this case, say if J is 0, it would be 2. So we would write 2 0 1 0. Oops. And So RC1 would be the low order bit, because we take this and we shift it 0 bits to the left. Here we shift it 1 bit to the left, and then we select the low order bit here by ANDing it with 1. Here we AND it with 2, so we select the second bit, and then we shift that second bit 1 bit to the left. And here we select the third bit, and we shift that 2 places to the left. And that gives us our 3-bit representation for RC1, RC2, and RC3. Yeah, actually, well, we don't actually have to do that. We could actually just set this equal to, we don't have to do the shifting function here. But we would have to do that if we were going to represent our RC1 as a 3-bit port. All right, and then when when our input clock goes back to, we wait here while it's 0, and then when it goes high again, we go back up and do the for loop again. All right, so yeah, so basically we do the for loop 6 times, and we output 6 different combinations here. Yeah. Okay. Yeah. Okay, so I made a little change here because we didn't really need to do the shifting. That was overkill. So this will just output the value for RC1, RC2, and RC3. Remembering that RC1 is the low order, RC2 is next, and RC3 is next. I think, or maybe I did it the other way here. Actually, I think here I did do it the other way. So I should fix that too. Okay, now it's right. So anyway, now of course, now the 2 sets of code do the same thing. So sorry for the confusion, but we've fixed that. All right, so let me move on here. So a 4-bit carry look-ahead adder. So I want to talk a little bit about the carry look-ahead adder. So let me just talk about this just a little bit first off. So in computing, as you all know, we talked about this earlier in the course. We looked at ripple carry adders, where we implement a ripple carry adder by taking a full adder. A full adder adds 1 bit of A, 1 bit of B, and a carry in bit, and generates a 1 sum bit and 1 carry out. Now, you can daisy chain these together, as we have earlier in the course, to make, say, a 4-bit adder or an 8-bit adder, or you could put 64 of them together and make a 64-bit adder. But here's the problem. The problem is that when we do this, if the more bits we have, the longer we have to take, because the first add operation has to completely run to either generate or not generate a carry out, so that the next bit can take that carry out as a carry in, and then it has to run to completion and either generates a carry out or it doesn't. And if it generates a carry out, that carry out then has to go to the next bit's carry in. And so you basically have to complete each bit before you can do the next bit. And that means that if we look back at this circuit, you can see we have here an exclusive OR gate for the sum, and for the carry out we have an AND gate here and an AND gate here and an OR gate. So we have 2 gates that it has to pass through before it generates the carry out. Fortunately, there's no case where we have 3 gates. But still, that means that every one of these adders can add 2 levels of gates, 2 layers of gates, before the carry out is good. So you have 2 gates here, 2 gates here, 2 gates here, 2 gates here. So if you have a 64-bit adder, you have 128 gates, that your last carry out has to go through potentially 128 gates before it's good. And that turns out to be way too long for an efficient adder in today's modern computers. So as a result, we definitely don't want to do that. We want to speed that process up. So how can we do that? Well, we can do what's called, there's a carry look-ahead adder, there are carry propagate adders. They kind of work somewhat similarly, very similar actually. And they look sort of like, this is a 4-bit carry look-ahead adder. And you can see, so here we have some 0 and some 1, some 2, some 3, and the carry out of the 4 bits. Notice the carry out has a lot of hardware. And notice the sum 0 just has a couple of gates and maybe an inverter or two. The sum 1 has a couple of 2 AND gates here. Well, another AND gate, it has a couple of layers here. And then as we go each bit, there are more and more bits, more and more gates involved, more and more gates, and finally a lot of gates. Imagine what this looks like if you've carried this out to 64 bits though. So the nice thing is, this means that all these outputs are good within just, so if you trace one through, and if you trace one of these through, you have an inverter here, and so you have 1 layer, 2 layers, maybe 3 layers worst case. There might be a case with 4 layers, I can't remember. Yeah, I guess there might be. Yeah, 1. Well, I don't know. Anyway, so we trace this through. There might be as much as 4 layers, but that's the worst case. As opposed to a 4-bit ripple adder, where you'd have 2 gates at each bit, so you'd have 2, 4, 6, 8 bits worst case. Whereas here, the worst case is maybe 4 gates, 4 layers. And that would continue to be true. Even as you add additional bits, you just have to have more and more and more hardware. The hardware increases at a very fast rate. So as a result, we generally can't afford to do a full 64-bit carry look-ahead adder. So we try and sort of compromise. So we have to compromise between efficiency and reasonable hardware investment. And usually what that does, we wind up with a mix. Maybe we do 4-bit look-aheads, and then we daisy chain them together to get, say, 8 bits or 12 or 16. And so, or maybe we do an 8-bit look-ahead, and we daisy chain those together to, say, 2 of them to get a 16, 4 of them to get a 32. And so we still have the 4, worst case, maybe 3 or 4 gates here, plus if we daisy chain them, then that may be 6 gates or maybe even 12 gates, but it's nothing like 128 gates. If, say, we did a 128 bit adder. So sometimes we'll do sort of a compromise between, we'll maybe do a 4-bit look ahead and then we'll daisy chain them, or maybe an 8-bit look ahead and daisy chain them. And usually we can come up with a good engineering solution to make that work. Okay. So finally, I want to do a little bit more complicated sequence detector problem. It's really, actually, it's not really that complicated or anything. So, but I think we'll try and do this. So here we have a, we want to detect a target of 4 1s in a row. And we are going to allow overlap between our targets. So, so if we did, I think I did a little, so our sequence detector then is 4 bits on 1. Maybe what I'll do, let me write some of this on paper. And we'll do I have here the SM chart, but let me develop a state graph for this, and I'll do that on paper. So, and let's see. Okay, hang on. Okay, so so our target's going to be 4 1s. 1, 1, 1, 1. Now, let's do a little test input sequence. Let's see, you have to see that though. So that's our target. But we are allowed overlapping targets. So if we have an input X and an output Z, Z is only supposed to equal 1 when we get a target. Overlapping targets are allowed, but it has to be 4 ones in a row. So let's say we get a 0 and a 1 and a 1 and then a 0 and then a 1, a 1, a 1, and a 1. Okay, so our 0 would be, our Z would be 0, 0, 0, 0, 0, 0, 0, 1. Because this is our first target. But then let's say we get another 1. Well, that would be another overlapping target, like that. So we get another 1. And then we get a 0, and then we get a 1. Okay, so then now we're back to zeros, and then a 1, and a 0, and 1, 1, 1, 1, and then a 0. So that'd be 0, 0, 0, 0, 0, 1, and then another 0. All right, so that's our little test sequence, and it's always good to do that. So we're going to have our block diagram. We're going to have our network here, and this is going to be a sequential network. We're going to have an input X, and we're going to have an output Z, where Z equals 1 when we get a target of 1, 1, 1, 1. So let's think our way through this then. So we start in S0 with nothing detected. We get one input. If we get a 0, we still have nothing detected. We'll stay here. Let's see, we were going to do this as a melee. So we'll output a 0. Now, a lot of times we'll just leave these off, and we only write in X when it's a 1, and we'll only write in Z when it's a 1. So otherwise we'll just leave that off. But if we get X equal 1, then we'll go to S1. And now we have the first 1. Now, that accounts for two paths, one where X is 1 and one where X is 0. Now we're in S1. If we get another 1, then we'll go to S2. And now we have two 1s. And then if we get another 1, we'll go to S3. And that'll be 3 1s. Now if we get one more 1, we can stay here, but we'll output Z equals 1. But if we get a 0, we're going all the way back here. And we won't have to write in X because we assume it's 0. And of course, if we won't have Z equals 1, so we'll assume it's 0. And then the same thing here if we get a 0, and the same thing here if we get a 0. So we'll just leave those blank. Or if you want, you can put X prime slash Z prime. Means X prime slash Z prime, and X prime slash Z prime, which means X and Z are both 0. All right. And here, if you want, you can put Z prime, and here you can put X prime, Z prime if you want. So, and here we'll do X, Z prime. But I think it's nicer if you declutter it and you don't put X prime or Z prime. You leave those out. You just leave Z out unless it's 1. Okay, so that's if we did it with a state graph. Now let's look at this SM chart. So with the SM chart, then it looks like this. And oh yeah, I think I do need yeah. Hang on. Yeah. Oh no, I need that. Okay. So here's the SM chart. So let me point this out. Okay. So in S0, we're gonna go to S0 on X equals 0, and we're gonna stay and on an X equals 1, we're going to S1, or we'll stay in S0 on a 0 and go to 1 on a 1. From 1 we'll go back to 0 on a 0 and to 2 on a 1. From 2 we'll go back to 0 on a 0 and to 3 on a 1. And from 3 we'll go back to 0 on a 0 and we'll go back to 3 on a 1, but we will output Z equals 1 at that point. And our state graph, you can see that. So on a 1 we go here, and the next one we go there, the next one we go here, and the next one we output Z and go back here. And if we get another 1, we'll output Z and go back here. If we get another one, we'll output Z. Or if we get a 0, we'll go all the way back. And here, if we get a 0, we go back. Here we get a 0, and here we get a 0. So you can see this is just a little more complicated than what we've done. And we're going to have some examples on the test that are similar to this, and we will work some more problems typically. But I want you to be able to kind of think through this with either using a state graph like we just went through, or using this SM chart. And then we can do straight binary flip-flop encoding. So this S0 would be coded as 0, 0. With 4 states, we need 2 flip-flops, so A and B, and then 0, 1, 1, 0, and 1, 1. And then you can just write the equations, and that's pretty much easy to do. All you have to do is just go through the process we had before, where for our DA input, you pick all the nodes where A is a 1, so that would be S2 and S3. And we get to S2 by A prime B X, and we get to S3 by A B prime X. And so we just OR those together, and that's our DA input. And then for the B, it's a 1 here, and it's a 1 here. So here, it would be A prime B prime X. There's only one path in, and here, there's only, well, here there's actually 2 paths in, and I left one out. One path, of course, comes A B prime X, but the other comes from here itself. It's a exits and goes back in, so it's A B X. So we have to add, for the X, we have to add A prime B X plus A B prime X plus A B X. And if you look down here, here it is, the DA, A prime BX plus ABX plus ABX prime, sorry, A prime BX plus AB prime X plus ABX. And that reduces to X times A plus B. And actually I didn't get my cursor showing. So notice we start in S0, and on 1 we go here, on 1 we go here, on 1 we go here, and then if we get another one, we output a Z with our conditional output box and back in here. Another one, we do this again. As long as we keep getting 1s, we'll stay in S3 and output Z as a 1. As soon as we get a 0, then we're going to go all the way back. And that's true for S2 and S1 and S0. We'll stay here on a 0. All right, our B input, same kind of thing. And then our output Z is really easy. So our DB input is just, we want to account for all the 1s, so it's here. So basically, all we have to do is drop this first term and replace it with A prime B prime X. And then the rest of the terms, A B prime X and A B X are the same because that's S3. And so our DB works out to be X times B prime plus A. And then our Z is really easy. It's just A, B, X. And that's the only time when Z equals 1. A, B, X. All right. So a few final thoughts. I've already mentioned this. When you design with FPGAs, many times you don't really have to simplify your logic expressions because you're going to be loading up truth tables. But when you design an application-specific integrated circuit, or if you're using an FPGA that doesn't have a lot of lookup tables, then you might want to simplify it. With an IC, you definitely want to simplify it as much as you can to reduce the surface area. And in some cases, it's good just to simplify your design so you can understand it better, because often once you boil down the logic, it makes more sense. So that's often true. All right, well, that pretty much completes what I wanted to cover for this chapter, and hopefully that gives you covers it pretty much, and it gives you a good overview. The only additional things to do are just to work more problems, to get more comfortable with more complex sequential designs, and over time, you'll probably spend a little more time looking at adders because they're so important, and especially higher speed adders, because that's what's used in pretty much all modern computing machinery today. Just simply because pure carry ripple adders are way too slow. Okay, with that, we'll quit, and we'll see you later.